and you are going to perform 10 experiments, out of which you are going to perform with your hands 8 experiments, and the remaining 2 are going to be demonstrated. Okay? Right in the very first class I mentioned to you that let whatever be the structure or whatever be the construction that we make in civil engineering practice, ultimately all the loads need to be get transferred to the underlying ground. Okay? So therefore, we civil engineers are interested in understanding when load is transferred to the ground, how is it going to behave. Okay? And out of all the materials that we handle in civil engineering practice, this is the one which is not made by us. And truly speaking, this was in its place for over millions of years before we bought. Okay? So whenever we are trying to disturb the state of equilibrium of this particular soil medium, which is as part of the ground in actual practice, we have to respect and understand what is going to be its engineering behavior. Okay? So incidentally, it cannot speak and tell this is my capacity or this is what is my behavior. We are trying to understand it through laboratory experiments. Okay? There are going to be 2 basic types of laboratory tests. The first category is going to be determination of index properties, and the second category is going to be determination of engineering properties. Okay? All these index properties have the objective of identification and classification of the soil medium. Why we need to identify, why we need to classify, we already discussed in the theory class. It is going to tell broadly what is my behavior. Okay? So in front of you I am going to show you 2 contrasting nature of soil mediums. Okay? So when you ask me why is it maroonish in color, why is it black in color, why is it having particles of different sizes, and when compared to this, again the particle sizes are different. Okay? When we talk about its engineering behavior, say for example, if I talk about this, with the help of my gentle thumb impression, I could able to pulverize this. With gentle thumb impression, I could able to pulverize this. But the moment I take this, in spite of my greater effort, also I am unable to pulverize this. So definitely you could able to understand that whatever particles are there, which we are calling soil solids, in this particular type of soil medium are not binded strongly. So therefore, with a little impression of thumb itself, we could able to separate them. But when we talk about this medium, it is going to be greater bonding. So in the sense, greater cohesion is there. So this is classical example of a cohesive soil, also known as clays. The classical example is clays. And when we talk about this, it is going to be relatively cohesionless. Okay? We have to rule out that there is no cohesion when we actually perform the shear strength test. Okay, you already know what is shear strength test. And when we come to know that C equal to 0, then we can call it as cohesionless. Okay, so similarly when phi equal to 0, we need to call it as cohesive soil. So coming back to the types of tests, index properties are always going to help us to classify and identify and classify. When it comes to engineering, definitely we are going to determine the engineering behavior with the objective of incorporating it in the design. Okay? Then fundamental thing which you should know in general as far as these 2 types of tests are concerned, as far as index properties are concerned, we are not bothered about the way the particles are arranged inside the soil mass. I already introduced all these terms. Just a quick recapitulation. Soil mass consisting of soil solids, and there is going to be unavoidable space present in between the particles, which we are going to call it as void. And our counterparts in what's called agricultural engineering, they call it as pores. Both are going to be same. Engineers prefer void, they prefer pore. We prefer to mathematically express it in terms of voids ratio, they prefer in terms of porosity. Both are interlinked, and you know very well from our chapter 1, what's called interrelationships, we already got n equal to e by 1 plus e equal to n by 1 minus n. Okay, these things you know very well. So now what we were discussing is, when it comes to index properties, all the index property tests are going to be conducted on the soil specimen, soil mass, soil specimen. Specimen, we use the term whenever we extract designated what's called soil content to perform a test, we call that as soil specimen. Okay, so this is soil sample, and what I am holding is going to be a soil lump. Okay, we also technically call it as soil mass. So now in this, as far as index properties are concerned, there is no necessity that the way the particles are arranged in the field is required, because the very nature of performing index tests is we are separating the particles and then performing their indicative properties. So therefore, there is no need of the way the particles are arranged in the field. But contrastingly, when it comes to engineering properties, after all, we are constructing a structure not in the laboratory but in the field. So when structure is built, loads are getting transferred to the soil medium the way it is present in the ground. So when you want to evaluate the engineering behavior, it is mandatory for us to ensure that the way the particles are arranged in the field are resembled in the laboratory soil specimen also. Okay, so the arrangement of particles matters when it comes to engineering properties. I told even in the regular theory class, for Fe415 there is going to be a modulus of elasticity 2 into 10 to the power of whatever it is, it's the unit. But when it comes to soils, strength is conditional. Okay, so it is dependent on soil structure, it is dependent on whether moisture is present inside or not, and so on and so forth. So fundamentally, engineering properties requires the soil structure and in situ moisture conditions. Okay, in simple layman's terms, unless we simulate the conditions present in the field, in the laboratory, the engineering properties obtained in the laboratory do not correspond to the ground in the field. That is the reason why we have to maintain parity between ground structure and then structure in the testing conditions. Okay, so this is fundamental difference. Now, as part of index properties, which we are going to take up today and maybe tomorrow also, there are going to be 5 fundamental properties. Number 1, it is going to be the specific gravity. Number 2, it is determination of water content. Number 3, particle size distribution analysis. Number 4, consistency limits. Okay, and of course in continuation we also learn how to find out the incident density using sand replacement method. All these have been discussed at length during our theory classes. Very quickly I am going to recapitulate and then mention to you the stepwise procedure. Done? Okay, so I demonstrated even in the previous class also. Just to appreciate that there is void space inside, okay, another phase, certain cc of water is allowed to enter into this medium, okay, and definitely this medium's total volume is not changing, and at the same time this medium is getting accommodated in some space inside this medium, indicating it is consisting of voids. And for your information, you should always have a mental visualization. Those voids are going to be of different size and different shapes, because particles themselves are of different size and different shapes. And definitely there will be connectivity, interconnectivity, and when we are allowing water to flow through, it will take a subcutaneous part. When we talk about day after tomorrow's work, how to find out permeability, we will spend greater time on that. So right now, straight away we are jumping on into the first experiment, that is going to be determination of specific gravity of soil solids. Okay, in the laboratory using 2 test procedures. Number 1, the density bottle method. Number 2, pipenometer method. Okay, so